proved entanglement distillation. Please take it away.
I think it was just on mute. Sorry. So I will tell you about new lower bounds on the two-way assisted quantum capacity for examples of Pauli and non-Pauli channels using an idea we call channel reshaping. So for example, for the amplitude damping channel, we're going to discuss reshaping the channel using constant weight encodings. And we will study a protocol, a heuristic called greedy recurrence for reshaping Pauli channels. And then we will use this reshaping idea to concatenate different schemes to get improved lower bounds for the depolarizing channel. But first, a quick refresher of some concepts in quantum communication and entanglement sharing. So depending on the setting, there's different allowed free classical communication resources. We can have an unassisted setting where the sender and receiver can only communicate through the quantum channel. That's, for example, relevant for communication in a quantum circuit. But you can have a setting where there's one-way communication from the sender to the receiver. And it turns out that the quantum capacity in the unassisted setting and this one-way assisted setting are equal. You can have feedback from the receiver to the sender, but not vice versa, or two-way assisted capacity. And due to the teleportation protocol, I will be speaking interchangeably of a quantum two-way assisted quantum capacity or two-way assisted entanglement sharing capacity, because up to some classical communication, one shared entangled pair can be converted into communicating one qubit. And we know of examples where the two-way assisted quantum capacity is strictly larger than the unassisted one. And a striking and important example is the quantum erasure channel, where we know that the unassisted capacity is upper bounded by 1 minus 2 times the erasure probability, but the two-way assisted capacity can be 1 minus the erasure probability with a very simple scheme where we just send the halves of unencoded entangled pairs, and using this backward communication, the receiver can signal to the sender which pairs were erased, and then they can use the leftover ones for communication. And there are some important entropic quantities that are used to quantify these entanglement sharing rates. So one of them is the coherent information, which is given by this expression, a difference of two entropies, and we optimize over the input state. So it's a difference between the entropy at the intended receiver minus the entropy of the state received at the environment through the complementary channel. And the coherent information is known as an achievable rate for the one-way assisted entanglement sharing. And just by switching the roles of the sender and receiver in the protocol that achieves the coherent information rate for entanglement distillation, we get a classical feedback assisted protocol which achieves a quantity called the reverse coherent information. So it has a similar expression, except the first entropy is evaluated at the input rather than at bulb's side. And for many channels, for example, Pauli channels evaluated at Bell states, these two will be equal, the reverse coherent information and the coherent information. But for example, for the amplitude damping channel, these might be different, for example, where the reverse coherent information is larger than the coherent information. So we will now look at the amplitude damping channel described by these Krauss operators and damping rate gamma. It's a practically relevant model because it models the energy decay from high energy level to a lower energy level. But it's also theoretically interesting because when we are usually working with Pauli channels, everything is unitary and unital, but the amplitude damping channel allows us to test these assumptions, like what happens when these assumptions are not there. And for a long time, the reverse coherent information was considered the best known lower bound for the two-way assisted capacity for the amplitude damping channel, but this is about to change. A very simple scheme that was used in previous works, which is called the dual rail encoding, has been shown to convert damping errors to erasure errors, and is used for quantum error correction settings. So in this scheme, we just encode a qubit in 2 qubits, and it's a Hamming weight 1 encoding. And if we look at the effect of the errors, of the damping errors on this encoded space, we note that it's either that the state gets scaled, or is mapped to an orthogonal subspace, or is completely annihilated. And this is similar to what the erasure channel does. So here we either get the state intact with some probability, or we are mapped to an orthogonal subspace, which we can test for. So just by this simple scheme, if we plot the yield we get here, so we will just, this is the probability, and this is because we use the channel 2 times. This is already larger than the reverse coherent information. So we can extend this and think about a triple rail encoding, and where we encode in 3 qubits and a Hamming weight 1 encoding, and then we get this slightly higher rate. And one might ask, okay, can't we do this for n qubits? And we notice that at n equals 3, like this is the maximum you can get for an integer number. So already the triple rail encoding is the best thing you can do for Hamming weight encoding. But you can still push this constant weight encoding idea further and try Hamming weight 2 encoding. So here I use this notation to mean that this is a bit string, like the ket of a bit string, which is all zeros except at the position number A and the position number B. And Hamming weight 2 encodings mean that we will have m strings, so that's n choose 2, and we can then use the protocol where Alice encodes an m-dimensional entangled state in this encoding of all Hamming weight 2 strings. Now when we look at the effect of of the amplitude damping channel on this encoded state, we will get something similar where to the previous case where the amplitude damping channel was reshaped into an erasure channel. Here the channel is reshaped into a direct sum of an erasure channel and an extra channel. So with some probability we just get the state directly. With some probability we get a separable state, so Bob can detect that we are in this orthogonal subspace because this is not a Hamming weight 2 state. And in the last state, this is the state that happens when there is a single A1 damping error. So then we look at this state, it would still be detectable on the receiver's side. So he will notice that his vector is a Hamming weight 1 vector. And he can signal using two-way communication to the sender that they are in this case, and they need to use the reverse coherent information protocol on this particular state. So overall, that we get the rate that with probability 1 minus gamma square, we get an m-dimensional entangled state. And in this state, we can extract this much entanglement using the reverse coherent information protocol. So now we will look at the difference between the yield of the schemes we propose and the reverse coherent information rate. So this is an improvement upon the reverse coherent information rate. So this triple rail encoding provides improvement in quite a large range, but we can extend that range by using this Hamming weight 2 encoding for 6 channel uses, or like 6 n equals 6. So now I'm done with the example of the amplitude damping channel. We will try to use the reshaping idea for Pauli channels. So for the case for entanglement distillation over Pauli channels, the problem can be mapped from trying to find an n-qubit Pauli error to trying to find a 2n-bit string. So we can make it a classical problem because each Pauli can be mapped to 2 bits. And many existing protocols just try to find this this error by doing various schemes involving measuring linear parity checks of this form. So this is equivalent to measuring a stabilizer, but we can also think of it as measuring a linear parity check. And using these ideas, there exists the hashing bound, which is the coherent information evaluated at a Bell state input. And it is achievable by a hashing protocol using one-way communication, where we need n times the entropy of the distribution of Pauli errors, random parity checks, to determine this string S. So these are sufficient because we will look at the typical strings. But we know that a two-way advantage is still possible, because in some ranges where the depolarizing channel is known to have a capacity 0, we can use a protocol called recurrence as a pre-processing step before moving on to this hashing step. And this recurrence step improves the input to the hashing protocol, and then we can get a non-zero two-way assisted rate. So what recurrence does, it reduces the entropy of this distribution of Pauli errors, and we can do it several times. So take the input accepted from one step and input it to another step of recurrence for some number of steps before switching over to the asymptotic protocol like hashing. And in this recurrence protocol, we need two-way assistance because Alice and Bob can cooperate to check if on a block of two Bell pairs, their error commutes or anti-commutes with the Z tensor Z. So this is also equivalent to measuring a linear parity check of this form. And then after measurement, if the states pass this check, so they're accepted, we lose one of the two pairs. So that's why if we cannot do recurrence infinitely, because then the rate would be 0. So we lose one of the two pairs, and the other one will have a new Pauli channel acting on it. So it kind of reshaped this channel. But if we are going to do many recurrence steps, maybe we don't want to keep checking the same type of error. So in the original protocol, it was suggested to do some rotation between the different steps. And we try to understand this in a more systematic way. So this rotation means that we are switching the type of check we are applying. And this greedy recurrence heuristic applies Q recurrence, so it checks for like Q tensor Q, whether the error commutes with this Q or tensor Q or not, whenever the input Pauli channel has the probability of the error Q as the smallest component. So we check for Y tensor Y when PY is the smallest, because that will catch all the other errors, the X and Z errors. And for this greedy recurrence protocol, we show that we have a guaranteed improvement of the entanglement fidelity with the greedy recurrence, and we show that among other choices, like the other Q recurrence choices at any step, it provides the largest improvement in entanglement fidelity. So other than the hashing protocol we discussed earlier, there are other asymptotic protocols like this one, which improves upon hashing, but even still this protocol requires these finite size pre-processing steps at the beginning. So it means these steps are important to extract the entanglement for the next steps. And these finite size pre-processing checks have been discussed for example, in this work. We focus on one of their best performing protocols, which is inspired by the 422 code, where we measure this Z tensor 4 check, and if it passes, we can measure the other stabilizer of the 422 code, and then we get a state which has two qubits, so they have now a correlated Pauli channel acting on them, but they are in an improved state, and now we can pass them on to any of the other asymptotic protocols. Otherwise, if we don't pass the first step, then we want to try to localize where the error occurred, and we do this check, and then we end up with only one pair left. So these protocols, we can look at compare their different performance, and we notice that this 422 inspired protocol outperforms the greedy recurrence steps in this intermediate noise regime, while the greedy recurrence is better at higher noise. And that makes sense. The greedy recurrence is checking for more errors. But you see, these protocols are quite also providing improvements on them has been difficult. So what we can think of is that since this 422 inspired protocol is slightly better than the greedy recurrence in the intermediate noise regime, we can try to concatenate these different protocols by thinking about them as that one of them has reshaped the channel into a better one. So if we do a few rounds of this recurrence, then we know that our channel is improved. So it's as if its parameter has moved a little bit to the left. So we can switch over to another protocol, which is optimal for this less noisy regime. And by doing this, we can obtain improvement upon all the existing protocols. So this is for the depolarizing channel, for example. So with this, we have shown some improvements on the two-way assisted entanglement sharing, lower bounds, but this opens up new questions. For example, for Pauli channels, we've mainly relied on these linear parity checks, and maybe there's something more possible to be obtained by trying to check for more general forms of checks. And maybe extending this reshaping idea can help us obtain further improvements on these lower bounds. Thank you.
Thanks for the talk. We have a lot of time for questions.
Hey, thanks for the talk. So I think last year or something, we had a paper with Francesco Mele and Vittorio Giovannetti on the continuous variable version of this, so like the thermal attenuator and the pure loss channel, right? Which is kind of the continuous variable version for bosonic systems of the amplitude damping or the generalized amplitude damping. So and also there we tried to use, we used also some dual rail protocols to try and optimize the rate, which hadn't been done before. And have you tried to kind of run your techniques also on this bosonic channels?
I have not tried for the continuous variable case. I know that there's this constant excitation cause. We're supposed to achieve a two-way capacity of the Gaussian amplitude damping channel, but I think like trying to map the two settings, I haven't tried yet, but I think it's
Thanks.
important.
Other questions? I have one. For the amplitude damping channel, you showed these plots, and the improvements were mostly for a large probability of amplitude damping. Mm-hmm. Do you have an intuition of why it works much better in that regime?
So my guess is that like we are kind of building, when we're converting to erasures, we're making like a detection of errors instead of trying to correct them. So maybe just not investing more energy in trying to find, not investing more into trying to try to correct the error and just discard. Maybe that makes more sense when there's more errors.
Final question.
I mean, maybe this is very naive. Does this channel reshaping perspective or this kind of way of thinking, does that also give new insight on the forward capacity, like the unassisted capacity?
So I think there exists an existing example. For example, this degenerate quantum Pauli channels, degenerate codes for quantum Pauli channels. It's an old paper, and I think they don't say it in these words, but I think there's this repetition call we do at the beginning, and then we do a hashing step, or like the coherent of information of this induced channel by the syndrome. So I think that's similar to what recurrence does. So I think in that case, it looks like a bit of a reshaping.
One follow-up question. For the departing channel, were you able to extend the threshold for the two-way capacity, or does it all meet at the same point still? You showed this one plot where you get close to the 0.5 point, right? Like it seems, do you know what's happening in the very, like around 0.45?
Not exactly, I think it's a numerical protocol.
I mean, we know that we can go all the way to 0.5, but the rates are just depressingly low.
Well, it is known that it goes all the way.
Sure.
Okay, then let's thank Dina again.